Welcome back, dear students. In last class, we studied the introduction. We come to know what is the compound stresses and what is complex stress. That is one and the same. The meaning of that and where we use this concept. Okay, that introduction part we covered. And in this class, there are two theories to study this compound stress and or complex stresses. Okay, the first thing is that this compound stress or complex stress will be effectively can be this effectively can be studied for three-dimensional bodies. Let us see what is that three-dimensional body is. See, this is the one body and it is in three dimension. Okay, now this is three-dimensional, and here I will mark x-axis, y-axis. Let us consider this perpendicular to the plane is the z-axis and vertical axis is the y-axis and this axis is the x-axis, right? Then this I can call this A, B, C, D, E, F, G. Here one point will be there, no? That inside that edge. This is G, H it is. This is a three-dimensional body. Then this ABCD is a XY plane. Will you agree? ABCD is XY plane. Right? Like that. Can you tell me which plane it is? BCGF. BCGF. BCGF is Z and Y. YZ plane it is. YZ plane. This is XY plane. Like that, these all six faces can be named by using X, Y and Z. Right? This is also YZ plane, and AEHD is also YZ plane, and this top one is what? This is XY plane. Sorry, XZ plane. This top one is XZ plane, and the bottom one is also XZ plane. Like that, we will be having three-dimensional body. On this three-dimensional body, we can put some forces. Those forces will be perpendicular to this plane, perpendicular to BFGC plane, and this I can call it as a sigma x, and this another that reaction force will be again sigma x, equal and opposite, to say it is in equilibrium. Then this force which is acting perpendicular to this plane will be sigma y, and the resisting force is also sigma y, and this force is a sigma z, sigma z. Okay, normal stresses are done. Now normal stresses are done. Now coming to the shear stress. Shear stress on this plane, which plane it is? First I will consider this XY plane. This is x-axis and this is a y-axis. Therefore, a shear stress can be acting this surface in horizontal wise. Then this shear stress I can mark it as tau xy. Tau xy. Tau xy, why? Because it is in x direction, and y xy plane. I can call it as a tau xy plane. Okay, and I can act another shear stress on this one, that is tau yx or xy. Okay, these two shear stresses I can mark here. Like that, here I can mark two shear stresses. Here I can mark two shear stresses. Here I can, like that, for all six surfaces I can mark shear stresses. But note is, very important note is, the sum of all shear stress must be equal to 0. Then sum of all normal stress must be equal to 0. The meaning is the body must be in equilibrium. When the body is in equilibrium, then only you can say that the stress is developed. Okay, when the body is in equilibrium, then only you can say the stress is developed. When the stress is developed, you can study that combination of normal stress and shear stress. Understood? This is very important point. Okay. Now, how many stresses are there here? That if I name them, then I have sigma x, sigma y, sigma z. Okay, and sigma x this direction, and this is also sigma x. Therefore, I will call only one. I will write only one sigma x. Like that, sigma y and sigma y, only one sigma y. Like that, I have three normal stresses. Three normal stresses. Agreed? Then how many shear stress will be there? Shear stress in xy plane, shear stress in yz plane, shear stress in zx plane. Three shear stresses are there. Look at here. If I take one small plane and one shear stress is acting, this shear stress is called as tau xy. If I call this is a tau xy, then there must be one resisting shear stress, that is a tau xy. Then only I can say that summation of fx equal to 0, right? This is going this side and this is going this side, both are equal and opposite, therefore the sum of all horizontal forces are 0. Like, but the body is not in equilibrium. This body is not in equilibrium. How? Because of this force and because of this force, I can say that this is acting like this is acting like this. Therefore, this body can rotate in this direction, can rotate like this in this direction. To stop this rotation, I need to apply one more force in the opposite direction. One more force in opposite direction, but in the shear only. Therefore, I have to show this and this arrows. These two arrows are creating anti-clockwise shear and these two arrows are creating clockwise shear. Therefore, the sum of all the shears will be equal to 0. Now I can say that the body is in equilibrium. Here very important thing is tau xy, and this is a tau xy obviously because this is a resisting force. This is applied force and this is the resisting force. No doubt. But what about the value of this one? This one if I call tau yx with a different name, then this tau yx is called as complementary shear. That is called as complementary shear. That is called as complementary shear. Okay, now you got complementary shear and shear stress, and all together the body is in equilibrium. I mean to say is here that sigma x, sigma y and sigma z normal stresses are there. Normal stresses are there. Like that tau xy, tau yz and tau zx. These three are shear stresses are there. Shear stresses are there. To counteract them, we have a complementary shear tau yx, tau zy and tau xz. They are complementary shears. Complementary shears. Like that you can call, there are, how many stresses are there here? There are 9 type of stresses are there. But for theoretically, tau xy must be equal to tau yx, tau zx equal to tau zy, yz equal to zy and tau zx equal to tau xz. Therefore, I can say that the three-dimensional body will be subjected to sigma x, sigma y, sigma z, next tau xy, tau yz, then tau zx. 3 normal stresses and 3 shear stress. The combination of these two is called as three-dimensional compound stress. Three-dimensional compound stress. Okay, now, but very important is you people are very small kids in civil engineering. You are small kids, newborn babies in civil engineering. Therefore, introducing this three-dimensional compound stress system is very, very difficult for you people. Therefore, for your study, two-dimensional plane theories are there. Two-dimensional are there. One-dimensional we will ignore it. The thickness of the material we will ignore it and we will study two-dimensional plane systems. And where this two-dimensional plane systems theories are applied, that I will explain later. Now you concentrate. We will not study this three-dimensional concept. Okay, we will reduce that study into two-dimensional concept and we will study. Okay. But theoretically or practically speaking, we don't have any plane structure. Everything will be having some thickness. Therefore, look at here. This is a plane, but the thickness is there, but that thickness I am assuming very small thickness, very small thickness. Then only I can say no, the stress is acting. Then this is called as sigma x. Okay, a small thickness is there here. Here it is acting sigma x. Then here it is acting sigma y. Then here it is acting sigma y. And there will be some shear stress here, shear stress here, shear stress here, shear stress here. This is a tau xy or tau yx. Okay, both are same. This is, and every time no need to show this thickness. This thickness is there. How much it is, this thickness is, that I will call it is a unit thickness. This is unit thickness. Now this become a plane, right? This become a plane. Now it is not a 3D space, it is not space, it is a plane. Having this plane word, we have a two type of theories. One is plane stress theory, and plane strain theory. Plane strain theory. Okay, they are different. Depending on your approach, depending on your requirement, we will go to plane stress theory or plane strain theory. We will go. Now one more thing, one conventional I am going to get a permission from you all, that every time I will not write this thickness, because this is a time consuming, writing like this and after that a small thickness like this. This is a time consuming, therefore I avoid that thickness. Whenever I write like this, you should understand that there is a unit thickness perpendicular to the plane. If I write only one plane like this, you should understand that there is a unit thickness perpendicular to the plane. Okay, now this is the conventional, this is understanding between you people and me. Understood? Now understand what is the plane stress theory and what is the plane strain theory. Coming to here, plane stress theory. Plane stress theory. Plane stress theory means your primary concentration is stress. When I say plane strain theory, then here the primary concentration is strain. This is a very general and common sense. That is, a plane stress theory means concentration is on stress primarily, and the strain means primarily stress. And what about secondary? When the stress is a primary concentration, then the secondary concentration will be strain. Means when I am applying stress, there will be a strain. There I can see some strain. Means, but stress is a primary function, first concentration, and the strain will be the secondary concentration. Like that, when you come to the plane strain theory, this strain is a primary concentration, but there also the stresses will be there. That is a secondary concentration. Okay, now just a minute. Okay, now in that also, how this theory will be studied and what are the assumptions we make in plane stress theory are, see, this is my plane. The first assumption in plane stress theory, that is, this is a plane. The first assumption is the body is in plane. Means the thickness perpendicular to paper or board is unit thickness. Okay, now the thickness perpendicular to plane or board is unit thickness, first point. And the second very important assumption in plane stress theory is, out of sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, out of these 6 components, sigma z is considered as 0 and the components with respect to z are considered 0. Means the stress perpendicular to the plane is 0. It is not there. Only sigma x and sigma y are there. Understood? Now look at here. Sigma x may produce epsilon x, strain in x direction. Stress in x direction may produce strain in x direction. Stress in y direction may produce strain in y direction. Stress in z direction may produce strain in z direction. Like that. Shear stress in xy plane can produce shear stress, strain in xy plane, shear strain in yz plane, shear strain in zx plane. When you come to the plane stress concept, you made this is 0, you made this is 0, you made this is 0. Very important. Seriously, listen here. Very important is, when you say sigma z is 0, it doesn't mean that there is no strain in the z direction. When you say sigma z is 0, it doesn't mean that epsilon z is 0. Therefore, means when sigma z is 0, then there will be a possibility that epsilon z can be present. Epsilon z can be present. Understood? That you need to think in a practical way. You only tell me, sir, how it is possible. हाँ, उसका बाप नहीं है लेकिन बेटा है ना. ये सिग्मा एक्स बाप है और सिग्मा जेड बेटा है. सिग्मा वाई बाप है और एप्सिलॉन वाई बेटा है. Like that, when sigma z is not, then how come this epsilon z can come? You tell me that reason, that whatever the knowledge I shared in the module 1 is helpful. You can, based on that, you can tell me the answer. How come this be possible? Like that, when this is not there, tau yz and tau zx is not there, but there is a possibility of having phi xy and phi zx. These two we can have in the system. Therefore, whenever I say a plane stress concept means, you should tell that the stress with respect to z direction are 0. The stress with respect to z direction are 0, not strain. You should not talk about strain. Right? Now coming to the plane strain concept. Plane strain concept, here again the main concentration is strain, 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 then strain, strain and strain. When I study it in plane strain concept, then I say that strain in z direction is 0. Then their parents will be stress, 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 stress in xy, stress in yz and stress in zx. Again, strain in z direction is 0 means this is 0, this is 0, this is 0. It doesn't mean that this is 0. It doesn't mean, very important, means when strain in x direction is there, strain in y direction is there, strain in z direction is not there, but still I can have sigma x, sigma y and sigma z, all three stresses. In z direction also I can have a stress. That again, how you need to think. Why I am leaving this to you people to think is, this is just a common sense. Just a common sense. It's not a science, or no need, you know that you people no need to think like a scientist. Just think in a common sense. You will come to know that I made strain in z direction is 0 means it doesn't mean that stress in z direction is 0. Otherwise it is not possible at all. If you consider this also 0 and this also 0 means it is impractically I am thinking. That you need to concentrate. And very important thing is, these two concepts cannot apply simultaneously on a body. You cannot say that, sir, one body is there, there are stresses are there in this direction. Can I apply plane stress concept and plane strain concept both at a time? Not possible. You cannot apply. Understood? But exceptional case is there. Exceptional, I don't know the spelling. Exceptional case is there. Exceptional case says that if your body is subjected to sigma x and sigma y with the condition saying sigma x equal to sigma y, very important, sigma x equal to sigma y, then you can implement both theories at a time or simultaneously. Understood? Both can be applied simultaneously. This is very, very, very important. Then the question is, sir, when we have to use plane stress theory and when we need to use plane strain theory? Important question, right? Very, very important question. See, when a material is there like a cylinder, this is a cylinder, and the cylinder surface is there here. This is a small plane I will consider on the cylinder surface. This small plane, its thickness is ignored, right? This is a thin cylinder. Thin cylinder means your perfume bottle. Perfume bottle is a cylinder and its thickness is very, very small. Your water bottle thickness is very small. Then there will be two type of stresses acting along the planes, but there won't be any stress acting perpendicular to the plane. Then in that case you can say that plane stress concept can be assumed. Plane stress concepts can be assumed. Here the stress in the perpendicular direction is not applying. Okay now, therefore sigma z you can ignore. You can ignore it. Understood? When you come to some other materials like thick cylinders, your some water tank or otherwise thermal power plants, this thickness is very, very thick, and if this thick cylinder is there like this is a thick cylinder. Okay, on that you are considering one plane. This plane will be like this, but comparing with respect to this area, this thickness can be ignored, but the strain in the z direction is ignored, but stress in the z direction cannot be ignored. That I will explain in the thick and thin cylinders chapter. Okay now, stress in the z direction cannot be ignored, but strain in the z direction can be ignored. Then strain in the z direction means epsilon z equal to 0, means you can apply here plane strain theory. Means in thick cylinders plane strain theory we can apply, in thin cylinders we can apply plane stress theory. Okay now, today this much is enough, and we'll go ahead with the next video that we will have a derivation, very interesting derivations from the next class. Thank you very much.